various applications. Okay, so today we discuss a sequence learning architecture. Sequence learning architecture. So we know that natural language problem, mainly if you are taking machine translation and whatever may be, all the data are sequential. Okay, for example, a sentence is running on the road. Bob is a nice person. So you can see that this is a continuous sentence. This is a sequence by sequence. Words are coming sequence by sequence. Okay. So these type of in order to process these type of sentences, because always NLP needs to process some sentences. Okay. The sentences may have different word length. So in order to process these sentences, we can utilize RNN, LSTM, or GRU. Okay. Normally, if the sentences are small, we can take the advantage of RNN. Why we can take the advantage of RNN is that, so you already discussed the RNN. RNN is capable of recognizing the words one by one. Okay, so it is repeating. You can give any number of words at a time. Okay, so architecture we discussed, but RNN, you can see the main problem that is coming under the RNNs are vanishing gradient and exploding gradient problem. Okay, so the thing is that if your sentence is of limited size, that means if your sentence may have maximum 10 words in a sentence, you can use RNN for different application. Why? The thing is that compared to LSTM and GRU, the complexity, the architecture complexity is less in the case of RNN. Okay, implementation point of view, time and space complexity, it is less in the case of RNN. But the main drawback of RNN is that it suffers a problem which is known as a vanishing gradient and exploding gradient. But if your sentence length, okay, if you can limit your sentence length, that is number of words in the sentence is maximum of 10 or something around that, you can utilize RNN. Why? Because you know that if the sentences are very high, if the length of the sentences are very high, there is a chance of exploding and vanishing gradient. But if the sentence length is very small, if you can limit it within a 10 length word, then that is okay, then fine, you can go for RNN. But if the sentences are too long, you can take the advantage of LSTM and GRU, because LSTM and GRU, last class we discussed how to avoid this vanishing and exploding gradient problem. Okay, so normally for application and sometimes we will tell RNN. Okay, so, but normally the thing is that if you want to replace it by LSTM, okay, fine, just replace it by LSTM. That's all. Okay, so for general sequence learning architecture, we can utilize RNN, LSTM, or GR. Anything it is possible. According to your data, you can use anything. So everything it is the NLP problem is according to your corpus. You have given a corpus, large collection of data, large collection of parallel data, it is known as corpus. So all the problems are depending upon your corpus size. Okay. So any sequence learning architecture, any sequence learning mechanism, we can utilize RNN, LSTM, or GRE. Okay, so most of the NLP application is using sequential data. Okay, so if you want to process sequential data, you have to use one of these architecture. Okay, it is flexible over various sequence of vectors. Okay, you can increase the number of inputs. That means it's not fixed. That is, if you are suddenly in the training phase, if you want to give a sentence which has different length, okay, so then it is easy for you if you are using LSTM or RNN. Okay, why? Because it is flexible. You can increase the number of inputs at any point of time. Okay, so any sequence learning architecture, any sequence learning problem that is coming under the natural language processing, you can utilize this type of architectures. Okay, so today we will discuss some of the application of natural language processing. How can you deal these type of application with the help of RNN and LSTM? Okay, so that is some another term, like we can see that some machine translation application like that we can implement with the help of this type of architecture. Okay, so this is the main thing, sequence learning with one RNN. Okay, you can see that there are different types of architecture. One to many, many to many, many to one, etc. Okay, so what about one-to-one classification? One-to-one classification for the thing is that these architecture can be suitable for different applications. That means one-to-one architecture can be suitable for one application. One-to-many can be suitable for some other application, and many-to-one and many-to-many, etc. Okay, there are some problems that can be utilized for using this architecture. For example, image classification. So image classification means you need to label an image for one label for one image. Okay, what architecture you can use? the one-to-one architecture, because there is one label for a one particular image. Okay, so one-to-one correspondence. If you go for the one-to-one correspondence, you can see this type of architecture. It is suitable. So this is you can think about this is an RNN. Okay, so this is a input, and you are going to hidden state and then output stage. This can be implemented. Okay, this is one-to-one architecture. This type of problems. Then some another set of problems. For example, image captioning. That means take an image and output a sentence of words. That means if you are looking the you can look at the picture, and from the picture you can conclude some sentences. Yes, this is the picture of something. This is the picture of an animal, or this is a picture of something. If you want to caption that particular image, that means input is only one image, but output may be a sentence. A sentence may be what it consists of more than one word. Okay, so input is only one thing and output is more. Okay, output is more means that may be a sentence. Sentence may consist of different word length. That's one. That is why if these type of application, you can take the advantage of one to many. One to many means one here. Okay, only one input, and that can be utilized. That can be outputted different thing. Okay, so you can see this one to many. So image to sentence, that type of application. Then another type of application. So this is known as a sentiment analysis. So you can see the sentiment analysis, some positive reviews and negative sentiments. Okay, for example, in Flipkart, and or if you are buying a product, you can see the okay, this product is good, this product is bad. Like there's comments, you can positive comments and negative comments. Okay, so in that case, you need to take different inputs. Okay, not one review. You had to consider different reviews, and from the review, you are analyzing that this is a positive or negative. Okay, that means you are taking more than one input. Okay, more than one input taking, and you are producing one thing as output. That may be a positive value or negative value, positive comment or negative comment. If you are going for that type of application, this subjects may be used many to one. So many inputs, many reviews. Okay, many reviews. From the many reviews, you are analyzing the review and you are producing a valid result. That result may be positive or negative. Okay, this type of application also possible with these all applications. You can see this is a sequence to sequence. Okay, some sequence of words, sequence of letters, sequence of characters, okay, anything. So, but maybe it may be it's anyway sequence sharing. In sequence maybe in the input or sequence maybe in the output, but sequence maybe in the input and output both. Still, it is possible. Okay, so that type of architecture is known as a many to one. Then many to many also. The perfect example for many to many, it is a machine translation. So what is a machine translation? Machine translation, you are taking some source sentence and you are producing a target sentence. Okay, so source sentence may consist of more number of words. Target sentence also consists of different words. That means word to word. Okay. When word means you can in a sentence you can have any number of words, isn't it? Yes. Your sentence may consist of 10 words, 50 words, 20 words, 100 words, anything. The output may also depends upon the target language. It also may consist of different kinds of words, a different set of words. That means 10 words, 20 words. That means it is a many to many inputs, and you are taking many outputs. This is also one type of architecture. That is an example of many to many architecture. Machine translation can be implemented with the help of RNN, LSTM, and GRU using many to many architecture. Whatever with the architecture, one to one, one to one, one to many to one, many to many, anything, any architecture, the important thing is that according to your data, again and again, I'm telling you have to study your corpus. You have to study your corpus, and you have to think what type of architecture is suitable for your data and your particular application. Okay, then you can take one of them. So these are the different set of examples. You can go for anything. Okay, but the one thing is that one main thing is that suppose you are taking a text. Okay, suppose you are taking a text. That means a sentence. So this sentence normally we discuss in the case of basic neural network also. So the same thing it is applicable here also. Why? Because you cannot directly give these sentences to the neural network directly. Why? Because neural network is accepting only zero cents. So that means binary values. Okay, it cannot take a sentence. It cannot handle a word. So what is the thing first it is needed? The main thing it is that you have to convert each and every word into vectors. Okay, so only these vectors can be inputted to the any type of architecture, whatever maybe one to one, one to many to many, etc. Okay, but the first thing is that you have to convert your each and every word that is occurred in a sentence into different vectors. Okay, so first of all, you have to take an algorithm that may be converting from what you have, that may be converted from word to vectors. You can utilize some already pre-trained corpus like word to vector or globe, anything you can utilize. Otherwise, if you want to implement your own algorithm, it is also fine. Okay, so whatever may be, you have to convert your input to vectors. That is the first thing. Okay, so that's why you can see here there is one. This is actually, these inputs are actually numbers. Okay, not, these are vectors, not direct words. These words should be converted into vectors, and these vectors is passing into the different architecture. Okay, that we will see. We will take one specific examples and we will see how this is happening. Okay, so then another type of sequence learning, it is that you can use multiple RNN. You can use multiple RNN, and that results a new architecture. It is same as the previous one, but this is known as a bidirectional RNN. So normally what we can see in the basic RNN is that you are reading the input from one by one. Okay, you are taking one word, then you are going to next word, next to next, like that. Okay, sequence modeling. But the thing is that if you it is possible to think a machine that is going forward and that is also coming back. Okay, that means you can see here there is an architecture. You are stacking the multiple RNN. Okay, so you can see one RNN is there. You are taking the input x0, then it is going to the neural network A. Then you are coming here. Then again this A is coming, going like this. This is a, this is a basic architecture. Okay, RNN, basic architecture of RNN. It is taking the inputs at any point of time, like x0, x1, x2, etc. up to xt. Okay, so this is a forward pass. This is you are going. This can be treated as a forward pass. But if you can think about, then you are going back, and from that you can design another RNN at the top of that. That is a B. You can see here it is B. So it is reading from backward direction. Okay, it is reading backward direction. So here it is forward direction, then you are reading backward direction. So here also you can see the input is x0, x1, x2, x3, etc. up to xt. And here this is hidden layers, hidden layers h0, h1, h2. So if this is architecture, what is the advantage of this architecture? The main advantage is that, so I already told you the nature of a word depends upon the words which is surrounding that particular word. Okay, so you will get an information, the word which is just next to the current word, and also you will get an information, a word which is just before the current word, because you are going forward and backward. Okay, that means if you want to analyze a word, okay, that word may be possessing certain property like a noun, verb, okay, whatever may be the property. If you want to analyze a word, you will get two information. Okay, the word which is after that and also word which is before that, if you are going for bidirectional RNN. Okay, so some applications, some natural language processing application may utilize this one in order to improve the efficiency. Okay, this is one type of variance of RNN. Okay, this is known as a bidirectional RNN. So normally you can go for many to many application. So all the many to many applications, you are going for this type of architecture. Okay, so this forward and also it is coming backward. That means it captures forward and backward information from the input sequence. That is a way it's thing. You can see this captures forward and backward information from the input sequence. Okay, that is case. Now, this is, you can see, this is another term which is known as a sequence to sequence model. Okay, we already discussed, we are already discussing sequence model. This model, it is known as a sequence to sequence model. I already told you that sequence to sequence model can be implemented with the help of RNN, LSTM, and GRU. If RNN suffers some problem, you can go for LST and GRU. Okay, so you can see here, there is a set of inputs x0, x1, x2, x3, etc. to xn. This is an input sequence, and this input sequence, okay, you are taking that information, you are taking some information, and you are going to some hidden state. You can see here some hidden state ht. You can see here, so some hidden state here. Okay, that means you are giving the input here. Okay, you are giving the input here one by one. Each and every timestamp you are giving the input. That means if you are, suppose if you are inputting a sentence, so the first word may come here, then next instance of time, the next word will come here, next instance of time, the next word will come here, like this. Okay, suppose I am going to market. Okay, something like this. I'm going to the market. Okay, suppose this is my input sentence. Okay, so each first timestamp, this I will come here and it is going here. Okay, so next timestamp, next word. Okay, it is coming the next input and you are inputting here. Okay, so the thing is that information, this you can see this information from this also it is coming here. Okay, so in order to take the information of this one, you may have three inputs. Okay, one thing is that it's on word, and also it is getting the hidden representation, and also it is getting the previous information. Okay, so next time stamp am is coming here, at the next time ham going it is coming here. Okay, then in order to predict the going, you may have both the information here and here. Like this you can input a sentence to a model. That model is maybe RNN. Okay, and this model it is termed as a one name which is known as a encoder. Okay, this model it is known as a encoder. Why? Because it is encoding some information. Okay, what you are encoding? You are encoding something from the given input. Okay, so this may be utilized for different applications. Okay, so this is known as an encoder. And after encoder, what final stage of the encoder, what he is doing is that he is representing a hidden representation of all the information that is already inputted here. Okay, so from this information, what is this information? So this is encoded as semantics here. Okay, encoded as semantics. Encoded as semantics means you are encoded something here. From the input sentence, you are encoding something here. And that encoded information you can utilize for the next stack of RNN, next sequence of RNN. You can see another RNN structure here. So that is B, next B like this. Okay, so input from B it is going here, and this is going here. This is what we are studying. This is RNN. And from this you are producing an output y0, y1, y2, y3, etc. yn. So these are known as outputs. Okay, so these are output, and these are known as a output, and these are also known as a decoder sequence. So this is known as a decoder sequence. Why it is a decoder sequence is that encoder is encoded something, and that information is passed to the decoder, and the decoder is decoding something with the help of the encoded information. So that encoded information may be anything. Okay, depends upon your application. That encoded information may be anything. So if you are going for machine translation, that may be some sequence of word structure or something like. Okay, so from that it is possible to identify the decoder, what may be the corresponding output. Okay, and this part it is known as an encoder, and this part it is known as a decoder. It is not independent, it is connected. Okay, from the encoded information only you are going to decode something. Okay, and this model it is generally known as a encoder-decoder model. Okay, encoder-decoder model. Encoder means extract and compress the semantic from the given input sequence. What do you mean by semantics? Semantic means semantic information. Okay, not syntactic information. I already told you that there are some semantic information, like the meaning of a particular word in a sentence may change according to the situation. Okay, there are a lot of ambiguous sentences. So in order to predict the correct meaning of the ambiguous sentences, you had to go for the semantic analysis. Okay, for example, last class, book that flight. Book that flight. In that sentence, book, what is the meaning of a book? Book, it is reading, you are reading a book. In that meaning, no, it is a noun or a verb. So it depends. Okay, in that case, book that flight. You need to book the flight, not the reading book. Okay, so you have to identify whether the book in that situation belongs to noun or verb. That is one example in the case of English language. And another case in the case of another English case also, English language also, I saw a man with a telescope. That is another example. Like Malayalam also, there are a lot of ambiguous sentences that we will discuss in the case of case studies. Okay, we can see a lot of ambiguous sentences in different languages. So whatever may be your target word, target language, and source language, you should be in a position to identify, you should be able to identify what type of ambiguous sentence may come in your architecture. Okay, so that is another research area. So depending upon their input and output in order to capture the semantic meaning. Okay, so the thing is that here you can see this is I'm explaining about encoded RNN. You can extract and compress the semantic from the input sequence. And then just opposite of encoder is a decoder. So the thing is that decoder generates a sequence based on the input semantics. Where you are getting this input semantics from the encoder. Okay, so encoder it can be encoder. It is always connected to the decoder. Decoder is decoding the information from the information that is available from encoder. Okay, this is mainly different types of tasks, but no, very important explanation of this one is a machine translation. Okay, this is a common example, machine translation. Why? Because machine translation, is giving a sequence of input as words, and also it is giving sequence of input as output. So this is a architecture. It is very suitable for this architecture. This architecture is very suitable for that type of application. Okay, so this is also, you can think about this is a sequence to sequence model, and also you can think about this is a many to many architecture. Okay, so we will see in implementation of encoder decoder in detail in the next coming slides. Okay, so this is just an introduction of the encoder decoder information. I think it is okay for you to understand the basic of encoder and decoder. Okay, so then we will see in detail what is the actual encoder and decoder. Okay, then okay, so this is the I already told you, this is the architecture, encoder decoder model. You have an encoder, you have a decoder here. Encoder, this is, you can have the input x1, x2, x3, and you can this hidden stage, and first LSTM it is going to the next h2, then h3, etc. Okay, you can have input and also some hidden vectors from the previous inputs. Okay, so you can get this information h2 from, if you going from in the h2, you will get an input h2 that is coming from here LSTM, this LSTM. This is continuously, this is encoder, and encoder, this is very important. This is known as an encoded vector. Encoded vector. Why? Because encoder is encoder some information. That information may be anything. Okay, anyway, that information should be a vector, because all things that is coming under the neural network is a vector. He's taking different types of vectors and processing the vectors, and he is outputting also some vector. Okay, and this vector, this value, it is very important. This vector value, encoded vector value. Why? Because this vector may contain some information. Okay, that may be some semantic, that maybe depends upon your architecture, depends upon your data, it may be anything. Whatever may be, this encoded vector, it is giving to the decoder. And according to the encoder vector, decoder is able to produce his own task. Okay, so decoder is exactly same as encoder. He is also taking same architecture, sequence to sequence model, and depends. Here you can see only 3 inputs and it is giving 2 inputs. It may happen. Sometimes it may be 3 inputs and you can have 4 inputs, 4 outputs, 5 output, 10 output, anything. It depends. That's already we discussed in the case of machine translation. He is running on the road. How many words? He is running on the road. 6 words. Suppose you are, somebody knows Malayalam. If you are going for Malayalam translation, avan roadil kude odikondirikkunnu. That means in English you have 6 words. In Malayalam you can have only 3 words. Okay. So that's why in that type of application, the input is 6. Input total number of words is 6. Output total number of words is 3. Okay. So in that case, that's why we are using RNN and LSTM. It is flexible. Okay, you can real-time examples can be taken. Okay, not a fixed size input. Input can vary. Output also can vary. Okay, it's not connection. There is no connection between the input and output. Okay, it depends upon your data. It can be anything. Okay, not always think that it should have 6 input length and 6 output, 10 input size and 10 output. Not like that. It can take any answer. Okay, any value. So this is the basic architecture. You can see encoder-decoder model. Once again, I already told you that this is input. You can see the input. So input can be anything. Here, actually, this I already told you that this can be utilized for any application. Okay. So here, this encoder-decoder model is explained in such a way that it is. I am in the encoder. I am giving something. What you are giving, you can see. I'm giving how are you. Okay. In output, you can see. It is again not the translation. So output, you can see this is an answer of that one. I am fine. Okay. So that is another application. What is another question answer instruction? That problem also, that means if you are giving an answer, you are asking a question and the neural network is supposed to give the answer of that question. There is no translation. So if you are giving an input is in English language, the output is also coming under the English language. Absolutely, there is no translation. But you can see that type of application also you can done with the help of encoder-decoder model. The thing is that whatever may be the problem, you can utilize the same encoder-decoder information into that problem. Nothing is changing. Okay, only the nature of the inputs and outputs are changing according to the problem. That means you know that there is some mathematical formula behind this one. Absolutely, there is no change in implementation. There is no change in formula if you are taking different classification problem. Different problems. So we will discuss the mathematics behind this one. You can at that time you can feel that absolutely the equation is not going to change according to your problem. That means if you have any number of problems, that problem can be explained with the help of encoder decoder problem, not on just machine translation, not sentimental analysis, nothing. Okay, you can give according to the your problem, you can modify your architecture. Here you can see input is how are you, the output is I am fine. Okay, so how you are giving this input, this is you can see how. Okay, how, and next you can see here how are you, and there is a actually this is important. Okay, this is why important means this shows the ending of your input sentence. Okay, not always question mark. Sometimes if you are going for some another application, that may be the end of sentence, like a full stop, anything you can be inserted. Okay, but here actually there is no information from here. Okay, so you can see that this is end of the sentence. This can be treated as end of the sentence. Now you got input how here in the first recurrent neural network, and here next word or next word you here. Okay, but this is you can, I already told you that this is not directly inputted to the recurrent neural network. Before, what you have to do, you have to convert this word to vectors. Okay, so that's why here you can have a encoder embedding layer. So what is embedding is doing? Embedding is doing is word embedding. Okay, word embedding. Its words are converted into vectors. You can use any type of vectors. Okay, so here it is words are converted into vectors. Okay, so these vectors are giving us the input. So this is not as a word embedding. Word embedding means all the information about the words are embedded here. So in word embedding, you can see any number of embedding. You can see any number of information can be incorporated in the words. Okay, like this may be some information. This may be some another information like that. This may be depends upon the word nature, like whether it is a noun, verb, etc., or this may be singular, plural, etc. So all the information about the word that is coming under the embedding layer. Okay, these words are converted into vectors. Each and every field of the vector has its own significance. Okay, so you can go for any word to vector algorithm, or otherwise you can implement your own algorithm. Okay, so anyway, it is now converted into word embedding are happening, and this word embedding, you can see here it is a vector. Okay, so this word embedding are giving to the recurrent neural network. Okay, so this is encoder in the encoder recurrent neural network. So encoder recurrent neural network. So you know this one. It's an RNN. It is connected to the next word. So this is connected to the next one, and this is connected to the next word. And here the incorporating this is end of sentences. So end of sentences you have here H0, H1, H2, H3, H4. Okay. So all the information you are coming here into Z. Okay. This is an encoder information. So here it is a encoder vector. Okay. So this encoder vector, it is coming into the decoder. Okay, in decoder, the thing is that here is the intelligence of this machine translation, this architecture. So what is the supposed outputs? Okay, so here the input is same. So you can think about the same architecture you can use for the machine translation. How can you change here? What may be the change here? So here you can see this is my input. Okay, here you can see this is my output. Okay, so in the training phase, you are giving in the decoder same sentence. So I'm fine. So that means if this is the input, this is the expected output. If this is the input, this is the expected output. So the thing is that if the encoder-decoder model, it is performing a translation, what may be the change here? So here you can change. The input is same. Okay, input is same language, but here if you are going for translation, instead of giving I am fine, you can give that target language like I am fine, enikku sugamanu in Malayalam. So that you can give here. Then the machine is trained in such a way that if you are giving this type of input, the decoder is able to produce that type of output. That's all. Nothing is going to change. Any mathematical formula, the input, output, everything is same. Okay, only the thing is that the input and output, the different data you are giving. Okay, the representation is same, everything is same. Okay, so from this encoded information, so this encoded information is going to decoder. So in the training phase, in the decoder, you can say this is a I'm fine, then I'm fine. So this is a start of the sentence. Okay, so here am. Okay, so in encoding, you can see first it is I. Okay, then this I information is coming here. Okay, next it is coming here into the first RN. So in order to predict the word am, so you get the what information? You get the information of the previous word, which is that previous word, this I. And also you will get the information about this encoded information. This is also you will get. Okay, so in next, now you predicted I am. Okay, then the next, this am, you can see it is coming here in the next RNN, it is coming here. So in order to predict the next word, you may get both information, because you already before the words are I and am. Then that means in order to predict the word fine, I get two information, I, then am, then after it is coming to fine. Then finally it is coming to the final end of the sentences. Here also very important that decoder should have a vector. Okay, that word should be converted into vector. And this is the decoder output layer. And this is decoder recurrent layer. This is recurring. And this is the embedding also should be done in the decoder also. So in embedding everything in word to vector or embedding layer, everything should be same in the encoder and decoder. Okay, because decoder is also giving a sequence of words. Neural network cannot process these sequence of words. You have to convert this word into vectors. Okay, so that type of architecture it is possible. And this is an application which is suitable for question answer section. According to your problem, you can utilize the same architecture for different problems. Then sometimes you will think out why I am using RNN. You can utilize LSTM also. Okay, depends upon that. Whatever may be your architecture, you can go for LSTM, RNN, whatever may be. Okay, if the data is very high, you can go for LSTM. Why you are going for RNN? Okay, so this can be easily replaced by LSTM. Okay, this is readily available in the, I think in the afternoon section, the code of RNN and LSTM, sometimes it may be discussed. It's very easy to implement RNN and LSTM because this is already available. You can utilize this one. Okay. So that is the thing about encoder-decoder model for this particular application. This means question and that answer is coming, question answer section. Okay. So, okay. Okay, this is another application of this one. Same thing, in any input activity sequence, you are giving same thing here. S0, S1 encoder. Here you are using GRU. So then after hidden, nothing is there, more same architecture here. The same thing you can use the output also. Then we will think about finally this one. There is a one thing, it is not a softmax. Okay, softmax we will discuss in the case of case study why we are using the softmax. Actually, this is a probability of the output. Okay, that already we discussed. If you are using for is using softmax. Okay, so that means the probability distribution over the output classes. Okay, in all the machine translation application, it's very fine if you are using softmax because output is a sequence of. Okay, that means probability distribution. The why we are using softmax is that it is a probability distribution over the output class. Okay, if you are using multi-class problem. Okay, single class problem it is okay, but if you are using multi-class problem, it is always used in all the natural language processing application. Most of the natural language processing application, you are going softmax. Okay, then also cross. There is a loss function, different type of loss function. Then here we are using a categorical cross entropy loss function. So different types of loss functions are there. According to your architecture, you can go for that. Also, we will discuss in the case study. What are the different types of optimizations, different types of loss function, etc. We will take in the case of case study. Okay. So this is a summary of what we have already discussed. LSTM, GR in RNN can be retain past information and update the gauge. And RNNs are more flexible architecture. It is real time and text processing, machine translation. Normally RNN means anything LSTM or GRU, anything. Text processing, machine translation, signal extraction, recognition, image capturing, mobile health or activity. Anywhere you can see this type of architecture. Okay. So these are the main architecture that is used in the NLP. Okay, now we will discuss in detail one application which is known as a machine translation. Okay, machine translation. So we will see, because I already told you in NLP there are different types of problems. Okay, you can text processing and like machine translation, speech processing, and sentimental analysis, word sense disambiguation, morphology, post tagging. Okay, different types of application are there. So today we will discuss in one. We will take one example, one application which is known as a machine translation, and we can see how this machine translation, what are the machine translation techniques available, and how we can utilize the neural network in order to produce the machine translation. If you are going for the neural network, normally the machine translation may result, it is known as a neural machine translation. Okay, neural machine translation. We will discuss the architecture of neural machine translation with encoder. Sometimes we may use encoder-decoder model, and also we will utilize encoder-decoder model. Slight modification of encoder-decoder model is also needed. Why? Because there is some problems in the encoder-decoder model. That problem we overcome with the help of another architecture like encoder-decoder model with attention. I think last class in the afternoon session yesterday might have discussed an encoder-decoder model with attention. And also that encoder-decoder model attention also replaced nowadays. It is known as another network which is known as a transformer network. Okay, so some additional features in the transformer network. That is the most commonly used thing nowadays for the machine translation. Okay, so here in the all the machine translation, so here there should be some source and target sentences. Okay, the case study, and also I am taking two Indian languages. Okay, in order to implement the machine translation. Why? Because if you are taking other foreign languages, if you are looking foreign languages, sometimes the machine translation may be easy. Why? Because in the machine translation process, the language features are very important. Okay, so if the language is fine, very easy, there is no complexity in the language, it is very easy to produce a translation. But it is not at all easy process if you are going for some complex languages, something like Malayalam, Tamil, Kannada, Sanskrit, etc. Why? Because you know that in Indian languages, okay, some of the Indian languages are very complex. Why? Because it is morphologically rich languages and also agglutinative languages. Why means morphologically rich language? We discussed yesterday what is morphology. Okay, so like a lot of sentences, lot of words are there which suffers a problem which is known as a morphology. Okay, lot of morphological aspects are there. So in order to implement the translation process, you cannot go for the direct translation. You have to consider all these factors. Morphology, also word sense disambiguation also very important. You have to identify whether the translated sentence may produce a correct answer. Okay, sometimes it may be a different answer according to your situation. Okay, so that whole thing you have to incorporate it. Okay, so normally we are using there are different technique. Here we are using corpus based approach. Okay, corpus based. What do you mean by corpus? What do you mean by corpus? In all the machine translation technique, we need a huge amount of corpus. What do you mean by corpus? A corpus means, generally a corpus you can think about. What do you corpus? Corpus, you can see that it is a large collection of data. Okay, corpuses. It is known as a corpus. Large collection of data. Large collection of data means in the machine translation. So here we are discussing in next lecture we are discussing only in the case of machine translation. Okay, we will forget other application like post tagging, morphology, like that. So we are dealing with only machine translation. Okay, so in machine translation, so there should be a source and target language. There should be a source and there should be a target. Okay, so very simple thing how we are doing machine translation is that there should be some source sentences. Okay, so these are some source sentences, and for each and every source sentences there is a target sentences. Okay, so this collection of this source and target sentences, collection of that, this one, it is known as a data collection. Okay, this is generally known as a corpus. Okay, so this is known as a corpus, large collection of data, and it should be a parallel corpus. Okay, parallel corpus. Why? Because it should be parallel. Why? Because if there is an input sentence, there should be a corresponding output sentence. Okay, otherwise you cannot train the model. There is an input sentence one, there is an output sentence. There is another input sentence corresponding, there is another output sentence. Like this, you have to define your parallel data. And also one thing, what is the length of this data? What is the length of this sentence? So this length can be anything. Okay, this length can be anything. So, but if the sentences is of very higher length, it is sometimes it may produce a bad result. Okay, so you have to process your data. You have to process your data in such a way that it should contain maximum of some number of words. Okay, if you're designing a corpus, one thing, it cannot be too large. Also, you can, if you can fix in some amount of words, that's also fine. Okay, so that means here it's on maximum words in a sentence is 15 that you can fix. Then here also maximum words, it may be less than that one. If you can design a corpus in that type of manner, it is well and good. Okay, and the thing is that there should be a parallel sentence. For this one, there should be some answers here. And for this next sentence, there should be a next target sentence here. For this source sentence, there should be a target sentence here. Like this, you have to arrange your corpus. Okay, you have to arrange your data. Okay, so if you can collect maximum sentences, the translation efficiency also high. Okay, but never think about designing a neural network if you have a 10,000 amount or 20,000 amount of data. Okay, at least you should have a minimum of 50,000 corpuses. Okay, if you can increase the number of corpuses, normally the translation efficiency also will be fine. So, okay, that is the case. Okay, so the thing is that what we are doing is that you are giving this source and target sentences for the training. Okay, you can see here the input is a Sanskrit sentence. Okay, it may be any sentence according to your language. You can give any sentence. So here it is a target sentence. Here it is I am taking Malayalam as a target sentence. And these two datas, okay, both Sanskrit and Malayalam, both source and target sentences are given for training. Okay, so and from the training, machine translation model, from the training in the machine translation model is finding some inferences. Okay, and with the data, so maximum, if more the data, more training will happen, more the flexibility of this model, more the efficiency of this model. And the testing phase, what we can do? In the testing phase, if you are giving a new sentences, the model should be able to produce the correct translated output. Okay, so that is this training, this type of training, it is very important. Okay, so using some measures, you can train the model. Sometimes it may be a probability, sometimes it may be some another thing. So if you are going for your neural network also, everything it is possible. Okay, nowadays we are going for the machine translator with the help of neural network only. All the training are done with the help of neural network. Before we have done some statistical machine translation. In that one, we are taking the probability and we are processing. Now it is, now everything it is neural network. Okay, that we will discuss. So this is just a theory. This is you can see a machine translation journey. So it is started in the 9th century, like different types of approaches, machine translation here. So we started with there is an approach which is known as a rule-based approach. Rule-based, you can see a rule-based machine translation. Then there is different models from different organization like IBM and also something like that. IBM models are there. Then another one, it is example-based machine translation, statistical-based machine translation. Now you can see there is a neural machine translation. Okay, so rule-based translation is there. Some problems may be there in the case of rule-based translation. So here also example-based translation. This is a corpus-based approach. Okay, this example-based and statistical machine translation and neural machine translation, all are corpus-based approach. But rule-based, it is not a corpus-based approach. It is following some rules that we will. In the next slide, I'm explaining what is rule-based approach. Okay, so here, so example-based approach. There are a lot of difficulties, a lot of problems in the example-based machine translation. That is replaced in the next architecture, which is known as a statistical machine translation. In the statistical machine translation, I am not covering the advantage and disadvantage of all this technique because this is already done before. Okay, you can easily get it through different papers. Okay, then in now the statistical machine translation, everything it is replaced by neural machine translation, and also still more unsolved problems in neural machine translation. So it is a open research area, neural machine translation. Okay, using neural network, you can go for the machine translation. Why? Because if you are taking the Google also, there is a Google translated. Translation is there, but it is not covering all the languages. You can see in between Sanskrit and Malayalam, there is no translation. If you are giving a Sanskrit sentence, it is not possible to generate a Malayalam sentence in the case of Google. Google translates, but English to some other language, something like it is there. So there is that's why it is known as a more unsolved problems are there. Okay. Now, so these are the, just quickly I will cover what are the different types of approaches. There are like rule-based approach. Okay, then there are some corpus-based approach. Now, neural network-based approach. So the rule-based approach is that this is what we can did before, rule-based approach. Rule-based approach is that, so it is generally taking the syntactic structure of a language. Okay, syntactic information of a language, syntactic information, syntax, syntactic information. So what do you mean by syntactic information? So each and every language is following some syntax. Okay, I think in the compiler design we did the phase which is known as a syntax analysis. Syntax analyzer is responsible for checking the grammar, checking the syntactic difference. So that means syntactic feature, it is possible to check the syntactic errors that is occurred in a program, okay, using different techniques. Okay, so that technique it is generally known as a process which is known as a parsing. Okay, you know something is known as a parsing. Okay, so what is parsing? Parsing, it is a process of checking whether the given sentence is correct or not with the help of given proper grammar rules that we know. Okay, parsing is the process of checking whether the given sentence is correct or not with the help of given proper grammar rules. So grammar rules, that is very important. Grammar. Okay, so then the grammar rules we are defining. What is a grammar? Grammar, it is a set of rules. Okay, different types of grammars are available in the compiler design. Also in the natural language processing also, different types of grammars are available. Okay, different types of grammars. For example, for English language, there is a set of grammar rules. And the set of grammar rules for the Malayalam language is exactly, not exactly saying, it is completely different from that of English language. So all the grammar rules, you need to incorporate all the grammar rules. And if you are going for a translation, that means for the, suppose you are going for English to Malayalam translation. Okay, English to Malayalam translation. So there is an English language, there is a Malayalam language. So English language, I am talking in the case of rule-based approach. Okay, rule-based. So in the English language, there is some syntactic feature of the English language. There is a grammar behind the English language. And in the Malayalam language also, there is some syntactic structure. Okay, so the syntactic differences between these languages can be formed with the help of rules. Okay, the syntactic difference should be captured with the help of rules. For example, English is following subject, verb, object, and Malayalam is following subject, object, verb. Very easy. He is running on the road. He is running on the road. Okay, so Malayalam, it is avan roadil kude ഓടിക്കൊണ്ടിരിക്കുന്നു. Okay, you can see that subject, verb, object. Here subject, object, verb. So you can see this is a difference in structure. Okay, so this type of structure, it is also different in the case of Malayalam and English. So these syntactic differences, like these syntactic differences, you had to find it out. Sometimes this may be S derives NPVP, noun phrase followed by verb phrase. But in Malayalam, it may be sentence may be derived from VP and P. Okay, so this I am explaining with the methodology. You may know this grammars and before in the compiler design. So what are the differences? It is not possible to cover all the what are the different types of grammar rules in this lecture. So you can refer what are the different types of rules that is formed in the English language like that. Okay, but this is generally noun phrase which is followed by verb phrase. But in Malayalam, it may be verb phrase followed by noun phrase. So this is known as syntactic differences. Okay, so you have to capture all the syntactic differences for the particular source and target language. And you can form the rules. Okay, if this sentence is coming, you have to produce a translation in such a way that it is capturing some another rules. Such a ways you have to define all the rules in the available for the source and target language. It depends upon your language. It depends upon your source and target language. Okay, so if you are using some complex language, the rules may be more. Okay, if it is a morphologically rich language, it is not at all easy to process set of rules. So it is simply, we can say that we cannot design a rule-based system for a complex language because the rules may be different. Rules may be very huge. If somebody knows Malayalam, so it's a Malayalam, it is a very complex language. Okay, very morphologically rich language. It is a agglutinate language. You can see rodal code still rodal code marathinde adil like this. There are a lot of sentences in there are. This is known as a chill words in the case of Malayalam. Chillashrang, that is we are talking in the case of Malayalam. Okay, so this type of morphological information may be needed in order to produce a translation. The conclusion is that this type of complex language we cannot form the rule-based approach, because if in the training base is okay, you form some rules, but in the testing phase, if somebody is giving with coming with a new sentence, new words, sometimes the rules may not be in your system will fail. So if the language is so complex, it is not at all possible to identify all the rules. Now the people will think about to avoid rule-based approach. Then we will train the system with the help of datas, corpuses. Okay, that we did in the last example, last case. It is known as a statistical based approach. Okay, you are with the help of statistical data, you are forming the translation. Now statistical based approach also some these type of things, morphology, etc. things are there in the case of any language. So then we compose last approach, it is known as a neural network based approach. In neural network based approach, you know that neural network, it is a black box. Okay, so you are giving the input and you are giving the out, you are taking the output, and the model is trained in such a way that it is possible to identify all the type of syntactic and semantic rules which is applied in the which is applicable in that language. Okay, then you can, if you can train with a lot of data, and neural machine is producing some amazing results. Okay, some wonderful results you can see in the case of neural network. Why? Because it is learning from the data. Okay, all the rules are automatically learning from the data. All the morphological rules are learning from the data. All the words and all the disambiguation sentences are also learning from data. And finally, translations are also learning from data. So if you have more number of data, the translation efficiency may be also high in the case of neural network. Okay, so we will talk about how this neural network can be applicable in the case of machine translation. Okay. So I already told you there is a neural machine translation. Neural networks are using for the translation, and in the neural machine translation, there are two models: direct neural machine translation, vanilla NMT model. It is generally known as NMT, neural machine translation, NMT, neural machine translation. Vanilla NMT model means you are simply giving neural network. That means here I can draw you something. Wait. So there is a machine. There is a neural machine. So there is a source. Okay. Then there is a neural machine model, NMT model. NMT model, you are giving targets. Okay, source and target before we discuss. So the thing is that this is known as a vanilla NMT model. So what do you mean by vanilla NMT model is that you are giving directly the source and target sentences, and neural network is trained in such a way that it is learning some rules from the source and target languages, and he is producing the outputs. This is known as a vanilla NMT model. Nothing is there. Okay, simple NMT model. So in simple NMT model, there is some modification it is possible. So that is known as a attention mechanism. We will discuss the attention mechanism. So we can incorporate this attention mechanism into the NMT. Then it is NMT with the attention mechanism. Okay. Then this NMT attention mechanism can be replaced by another model which is known as a transformer network. This is more advanced model compared to that of NMT with attention. That's also possible. Okay, we will see both. So neural machine translation, I already told you, it is giving source and target. From the source and target language, it is producing outputs. Okay, so this is the main thing. In neural machine translation, we using Encoder-Decoder Model. Okay, neural machine translation is generally it is an automatic translation with the help of deep neural network, and NMT uses encoder and decoder. For the, I already explained you encoder and decoder model. That encoder and decoder model, it is utilized in the neural machine translation, and also some attention mechanism, also transformer approach is possible. So you can see here. So this is exactly what explained before. It can be encoder reading the inputs. Okay, this is Paiha Pipadi. This is a source sentences, and he is encoded that information, and here you can see a vector. That vector it is giving to a decoder, and decoder it is able to produce the output sentences. Yeah. Okay, so this is the from the last encoder state, it is giving to the input of the decoder. Okay, so this phase it is known as a language generation, and first phase it is known as a language understanding. Encoder understand the language understanding, and next one it is known as a language generation. Okay, this is exactly what is happening. So suppose the source sentences are, this is the NMT model. This is an exact representation of NMT model. Here, this is in the training phase. Okay, so this is A, B, C, D. These are all of words of a source sentences, and this is giving to the recurrent neural network. And from the recurrent neural network, this is the translated output. So in the translation also you are giving, here it is going X, okay, output. Then it is, this X is coming, actually coming here, and this Y it is coming to here, like this. It is producing the translation, and this is the end of the sentences. Okay, so this is the basic NMT model, neural machine translation model. So like this is exactly what I explained here. That last one, it is known as a context vector. Last vector, it is the information from information from the source sentences is encoded into a vector. That vector it is only known as a context vector. Okay, from the context vector it is possible to for the decoder for the generating the target sentences. Okay, so you can see first in first timestamp. Okay, so then first timestamp, you can see a word, and economic growth has slowed down in recent years, full stop. Okay, so this word it is giving to this encoding. Okay, so this is word is encoded, it is converted into vectors, then word embedding it is done. Okay, and next timestamp you can give the next word, in the next timestamp you can give the next word, like this. Okay, so the information you can pass here. First word information is going to first hidden layer, and in order to implement the second hidden layer, you can take the information from the first hidden layer, and this continues. For the third word, it is coming in the next, like this. Information is flowing. Okay, so you can see this information is coming here, and here it is going here, and finally it is, you can see in final stage the information is here. Okay, in the, you can see in the encoder, full stop, this is end of sentences, this is known as a context vector. Okay, so information is coming here. So from the information here, you are possible to decode the sentence. Okay, so you can see the final thing, it is final information from all this. Economic growth has slowed down in recent years. Up to here it is words, these words are represented, and all the information it is here in the next context vector. So in the last thing, it is a full stop, that end of sentences, that can be treated as an encode, that can be treated as a context vector. From this context vector, where you can give this detail I explained, from this context vector you are giving to the target sentence. So you can see this is T1, T2, T3, T4, T5. These are the target sentence length. Okay, so this information, you can see this information, it is going here. So in order to implement next one, you are coming here also, and here hidden state also following the previous words, also information is also coming here. Its own hidden state, it said its own hidden state, information from the previous hidden state, information from the previous layer, it is also coming here in order to produce the next word. So decoder, each and every timestamp, the decoder is possible to identify the corrected translated output. Okay, so this is what exactly what is doing in the encoder-decoder model. You can see this is encoder, and this is encoded information here, and from the encoder, from the context vector, the encoder is possible to decode the information. Okay, so this we can think about the equation encoder. So encoder, it is a hidden vectors. Okay, hidden layers can be HT. It can be found that it is a function of, it is a weight matrix of the previous HT minus 1 plus the current input. Okay, this is weight matrix of the HT minus 1, previous hidden layer, and also the current input, that is encoder. Isn't it? You can see this information. In order to get this information, you may get the information of the previous hidden state, although the current time input. Okay, current input. That is XT and HT minus 1. XT and HT minus 1. That is the encoder information. And from the decoder, what you are getting, you can see in the decoder information, you are taking from the hidden stage, previous hidden stage. From the hidden, you can see the previous hidden state. All the information is coming in the previous hidden stage. That means information from the previous state is also coming here, and that information is here. And you can easily, HT minus A, you can decode the information. And finally, I already told you that you are taking the probability distribution of the output, then you can take the softmax of that particular thing in order to produce the output. Okay, output you can see is softmax of that. So the thing is that this equation is common for all the application. I already explained that this can be utilized for question answering section or image modeling, anything can be utilized. Okay, but the equation remains same. Only the thing is that you are changing your data. According to the nature of the data, the neural network is able to produce any type of translation. So not translation, any type of model, any type of problem. That model can be readjusted in such a way that it is produced to give the output. Okay, so this is the basic thing about the encoder-decoder model, and this is how the encoder-decoder model can be utilized for the machine translation. But the thing is that you need a large amount of corpus in the source data and also in the target sentences. And so there is a one drawback of this, which one? Vanilla NMT or encoder-decoder model. So the vanilla sequence to sequence encoder-decoder model, input is a fixed dimensional representation, that is a sort of stating encoded was the last in. That means you can see here, so the decoder is getting the information, okay, only after reading all the words from the encoder, and that encoded information, but there is a single representation for the encoded information. There is no separate representation for each and every word, isn't it, in the encoder model? Because this is coming here and coming here and coming here, and finally this context vector will hold all the information about the previous word. That is a single vector. But the decoder doesn't have any information about each and every single word. Okay, suppose in a translation, some translation may consist of different words. Sometimes it may be a 50 or 40 words. Okay, if you are going for the translation of that type of sentences, then some words may get higher priority. Okay, some words may need more priority than that of other words, because the importance of that words are more in the case of a sentence. Okay, but in the encoder-decoder model, we are not giving importance to any word. It is giving equal importance to all the words, and all the information is coming here, and all the information is stored in the final context vector here, isn't it? Final context vector. But if it is a good mechanism, it may be a good mechanism if you can give some importance for the some words. Okay, for example, in some translations, some words may highlight, some words may be needed, some words may be more needed for the translation, some important words. So if you can give some importance for the words, some weightage for the words, and that weightage can be passed in the decoder. Decoder is able to identify the importance of word in that situation, and according to that, he can make the translation more efficiently. Okay, that is not done in the case of encoder-decoder model. Okay, so that can be incorporated in another mechanism, which is known as a attention mechanism. Attention, we are giving attention to some certain words. You know the word attention. Attention, somebody is getting attention. Okay, so I am giving attention to some words which may give higher priority. Okay, so this is a very simple that one. So you can see there is no single context vector here. Okay, so before that, the encoder, each and every encoder, you can see each and every encoder, there is a connection to the one vector which is known as attention. So this attention vector, there is, you can see some connections here. There are, you can draw here. You can see here there are each and every word it is connected, isn't it? Here it is connected. Here it is connected, here it is connected, and this connection maybe it should be assigned by some weights. Okay, so connection means it should be assigned by some weights. So if you are giving more weight to this word, suppose you are giving more weight to this one, more attention will be coming to for this words. Suppose you can give less attention, less weight for this one, less attention may come here. So you can fix the weight here. Okay, so more important word can be given to the more weights. So according to the attention model will give some score. Okay, some score, attention score. So we will discuss in what is an attention score. Using this attention score, you can see in the decoder here, this is also coming here. Okay, this information is also coming in the decoder. So basically it is coming to the context vector. This context vector is also giving to the decoder. So the decoder will have the information about the attention score also. So using this attention score and also the current context vector, decoder can produce a translation more efficiently. So this is important. And how can you assign this weight? How can you know that this word is important? Who is giving this weight? This is also the responsibility of neural network to find automatically the weight of the corresponding connection. Okay, so this is also a important how these weights are learning in the case of neural network. Okay, neural network itself is finding weights and giving more importance to the some words, and according to that you are putting an attention mechanism, attention score. From the attention you can produce the translation. Okay, so why last hidden stage? Take all the hidden state and make it available. A pool of search states. That is the main motivation behind this one. Why last hidden state? No need to go for the state hidden state. Take all the hidden states and make it available. Okay, all the hidden state and make it available. That's the thing. So we'll see some equations behind the attention, some mathematical behind the attention. So there is an attention score. That is important, attention score. So attention score is based on the previous hidden layer and the current hidden layer. The scoring function will score in each position and where to pay the attention. So according to this score, we are giving each position, we are giving the attention. Okay, in each and every position, we are giving the score. So build a representation which combine all the memories weighted by the score. According to the score only, you will get the output. And finally, you can apply softmax to give the probability distribution over the attention of different places of source. That you can see here, attention here. So this one, this CI, you can see this is a attention layer. Okay, so this attention layer, it is combining different hidden layers. Okay, H1, we'll draw here. So here, this is an attention layer. Okay, so this is attention layer CI. You can see here CI. What we are doing, then combine together all the hidden state of the encoder weighted by how much attention is needed. Okay, so this alpha ij shows how much attention is needed. And Hj means hidden states, each hidden state. It is varying, J you can vary according to the timestamp J equal to 1 to Tx. Okay, so alpha I already explained to you, this is how much attention. Okay, how much attention I have to give to this verb. Then this is a hidden layer. And CA it is known as a context vector. Okay, so in order to produce the context vector, you are taking so much a factor which is known as attention. Okay, so here you can see this factor, this context vector, it is a summation of J equal to 1 to Tx, total timestamp, alpha ij into Hj. So alpha ij, this is how much attention into corresponding hidden layer. So how much attention I am giving to this corresponding hidden layer. This H may vary, H1, H2, H3, etc. up to HTX. Alpha ij also may vary. Okay, alpha 1, alpha 2, alpha 3, this you can see this is alpha here. Alpha I. Okay, this is alpha I. It is constant here. Okay, only one alpha. So alpha ij, J it is varying. So it may be H1, it may be taking H2. All the information you can see is coming here. All the information is coming and summing here. Okay, you can hear the summation sigma. So from this context vector, this is at an attention layer. It is giving that attention to the target centers. This target sensors, y1, y2, y3, the remaining mechanism is same. Okay, it is giving here, it is giving back here, and this is producing. Okay, so this is attention mechanism, giving importance for some words. Okay, some important words. The thing is that how do we score? We already discussed. Take a dot product between the decoder hidden state and encoder hidden state, word with the same meaning. Okay. The thing is that here more mathematical behind this one. The score can be this can be explained as this is a weight vector can be HT. This one weight, this decoder weight HT dot products hidden state and this source state. And score HT HS can be, you can take a weight matrix here, okay, and weight matrix according to the hidden state, and you are just giving a transport in order to make the dimension correct. HT transpose WA HS. Okay, from that you are giving a softmax, the tan HTs you are taking and concatenate in order to produce this context vector. Okay, so this is how the global attention mechanism it is. So initially encoder-decoder model, and this encoder-decoder model, it is supported by a global attention mechanism. Okay, so that way you can see NMT model is also replaced by attention mechanism. So you can see all the information, not like before. So all the information is coming here. It is going to a context vector, and from this context vector, you are giving a attention. Okay, in the each and everything, it is attention model is coming. Okay, so this is what we explained, attention mechanism. So basically we covered neural machine translation, and neural machine translation, I already told you that there are some problems that is end up with the NMT with the attention mechanism, encoder decoder with attention mechanism. Now you can see that the more implementation that is known as a neural machine translation with a transformer network. You can see the transformer network, it is somewhat it is similar to the encoder-decoder architecture, but it is a stacked information you can see here. Okay, more you can say this is an important thing. Positional encoding is also done in the stacked encoder-decoder model. Okay, so you can see encoder 1, then it is going to encoder 2, then multiple words can be processed at a time. Okay, that is multiple words can be processed. More than one word can be processed with the help of transformer. Okay, that's why you can see here different types of encoder, different decoders, and also you can see some self-attention mechanism is there. Still, it is forward network is there. So one important thing is that you are incorporating positional encoding here. Positional encoding means position of a word in the particular sentence is also incorporated in this transformer network in order to produce output. Okay, I think in the afternoon class, so we cover how to implement the transformer network and the more implementation details of the transformer network. Okay, so this is exactly what we did. And that is a translation from Sanskrit to Malayalam. Sanskrit sentences, Malayalam sentences. This is known as an attention mechanism, and you can see this is actually what is here. Input sentences, this is converting into a joint character word embedding, then hidden layers, then attention mechanism, and finally softmax layer in order to produce the output. Okay, so that is the main. Some applications are done with the help of natural language processing, especially neural machine translation. Okay, so the neural machine translation we are utilizing vanilla encoder-decoder model, encoder-decoder sequence-to-sequence model, sequence-to-sequence model for the translation purposes. Okay, so this you can think about any languages, Now, the next session after the break, we can take one specific example. Okay, one source and target sentences, and how can we apply these type of translations? How it is possible to do translation with the help of some language pairs. Okay, we will design some issues of some languages, and according to you have to solve that issue before the translation process. Okay, so that we will cover after break. Namita, shall we go for a break?
Sir. Okay, sir.
So before that, any doubt up to this, please ask. Then we can.
Participants, you can ask your doubts now. If you have any doubt, you can ask now.
Otherwise, we will think about after covering the next session also. Okay, that we can plan, Narita. After the break, after the next session, we can go for the question session. Okay.
Okay, sir. Okay, sir.
Then okay, we can come back by I think it is 11:20, 11:35. Okay.
Okay, sir. You can
Okay.
start our. We can continue this session from 11:35 onwards. Okay,
Okay.
everyone.
Okay. Okay.
Now you can leave. Okay, sir.
Okay, welcome. Mother, shall we start?
Yes, sir.
Screen is visible, right?
Yes. Visible.
Okay. So next we will discuss neural machine translation with the help of two language pair, with the help of interlanguage pair, which is Sanskrit and Malayalam. Okay. So you can think about conversion from Sanskrit to Malayalam or from Malayalam to Sanskrit, both. Okay. So why the this translation it is very important is that so main thing what are the challenges of this machine translation is that so there are a lot of ambiguity, order of the sentences, morphology, and unavailability of standard corpuses. Okay, I already explained you that in order to perform neural machine translation, we need a huge collection of data. Okay, so for this work, actually, ready-made data is not available. So in order to implement these two language pair, these two languages, we need to develop our own corpus. Okay, so you have to design your own corpus. So whatever may be your research, so according to the research, according to the source and target language, you should be able to generate the data. Okay, for this work, if the data is available, then we can go for any type of translation. Okay, so here some ambiguous words are there in the case of Sanskrit and Malayalam sentences. Also, order of the sentence is different because Malayalam, you know, this is a subject object verb. Then Sanskrit is a free word order language. You can fix the order in any type of mechanism. So morphology is there. Both are morphologically rich languages. That's why the machine translation is important. Okay. So the thing is that if you are going for a research, that translation should not be there in any that. Okay. So in Google Translation also between Sanskrit and Malayalam there is no translation. There is no translation. Okay. So this is actually what we are looking for. Okay. So this one we discuss transformer NMT model. Okay, NMT model we discuss. But if you are giving a source and a target sentence for here, if you are giving a Malayalam and Sanskrit sentences for neural machine translation for vanilla NMT model, it will result a poor translation efficiency. Okay, why? Because the neural machine translation (NMT) it is designed in such a way that if source and targets are of same features. Okay, for example, any foreign languages, a source suppose take a source and target languages. Source language may contains 5 words, the target language may contains exactly 5 words. Then you can see very mapping it is very easy. One-to-one mapping is easy. One-to-one mapping can be possible. So there is a one word, one source word, there is a corresponding target word. And also the word absolutely it is almost same in the case of syntactic features. That means the morphology is very less in the case of foreign languages. Okay, so very easy to map between two foreign languages. Okay, then also one more thing is that it almost uses the same word order. That means one is following subject verb object, the other one is also following subject verb object. In that case, if everything is fine, everything is in order, you can utilize the NFT and you can see NFT is producing some wonderful results. But unfortunately, in Indian languages, this type of system is not applicable. Why? Because of there are certain features of the language. First feature we already discussed is known as morphology, and another one is known as word ambiguation. Okay, ambiguous sentences. So what we have to do, the vanilla NMT model, it's showing a poor performance. So you had to pre-process your data or post-process your data in order to make the translation more efficient. Okay, so how can you do that one? So the thing is that you can see here, NMT model, there is some pre-processing agent. This is some pre-processing. Okay, and after NMT model, there are some post-processing. Then only output it is coming. It is okay. So this block, it is you can see it is an automatic language identification module. So this block it is not an important thing because it is automatically identify a language whether because I already told you this is a system which can convert Sanskrit to Malayalam and also from Malayalam to Sanskrit. So in order to identify which language is inputted, there is a automatic language identification model. Okay, so after language identification model, you have a Sanskrit sentence and Malayalam sentence. But before NMT model, you can see here a morphology is there. Okay, we are here. It is a morphology. You can see a Sanskrit morphology and also Malayalam morphology. Okay, so why Sanskrit morphology should be done and Malayalam morphology should be implemented before NMT is that both Sanskrit and Malayalam sentences are morphologically rich languages. Okay, so if you are not applying the morphology, translation may result a poor translation efficiency. So before the NMT model is predicting the result, you have to process your data in such a way that all the input means all the corpuses should be morphologically separated. It should be done in both Malayalam and Sanskrit, both source and target. Okay, so you can think about your own system, but the thing is that you have to identify all the morphological rules that is coming in your language, do morphology in both those both source and target sentences. So after splitting the data, after applying the morphological analysis in source and target sentences, here it is Sanskrit and Malayalam sentences. Next thing what you can do is that you can pre-process the sentence. That means a one-to-one alignment can be mapped if it is possible. If one-to-one alignment can be mapped, it is well and good. But in some languages, it may not be possible. For example, for English language, he is running on the road. We cannot write he on the road is running. Okay, why? Because the syntactic features never allows that. Because that is a syntactic rule that is followed in the English language because it is following some grammar rules. But sometimes some languages may change the word order without affecting the total meaning of the sentences. So here in this case, Sanskrit is known as a pre-word order language. You can frame the words in such a way that you can alter the words. You can rearrange the words in a sentence. Then the meaning of the sentence still remains the same. If that kind of thing it is possible, you can think about that type of processing before the NMT model is going to train, before training of the NMT model. So what you can do is you can do a morphology in source language, and also you can do a morphology in target language, and into that you can apply some pre-processing, some word alignment or sentence alignment, and after sentence alignment you can give it to a model. That model can be encoder-decoder model, encoder-decoder model with attention model, or transformer model. Okay, so transformer model is the latest one, so we can go for the transformer NMT. So I already told you that in NMT, how you are giving the data? You are converting, there is a word embedding representation. That word embedding, it is important. Why? Because the word embedding, it is able to identify all the syntactic and semantic features that is occurred in the word. In order to capture the semantic meaning, we are using the word embeddings. Okay, so still you know that according to your source and target language, if you can represent more semantic features, that is well and good. Okay, so what word embedding is doing? Word, it is depending on the word, the character of the word, the nature of the word is identifying, the semantic is identifying, the gender is identifying, and all the information you are processing with the words. But what modification you can think about that? There is another mechanism which is known as a character embedding. Okay, character embedding, word embedding, and character embedding. So difference is that in word embedding, words are going to embed. In character embedding, characters are going to embed. So each and every word there is a representation in word embedding. In character embedding, for each and every character there is a representation. Okay, so these languages, if your languages are syntactically and semantically rich language, that means morphologically rich language, it is well and good if you can incorporate more character features in your languages, in your representation. Okay, so you have to, if you can incorporate word representation, also character representation, that combination will make you a great result. Okay, that's why you can see before word representing, you can what in here in this method, what we can do is that you can go for a joint character word embedding mechanism. Okay, joint character word embedding mechanism. Normally it is a word embedding, or sometimes it may be a character embedding. If you want to incorporate more both you can go for a joint. So how can you join this one? So that we will discuss how can you join this character and word embedding. If you can do that one, this is good. Okay, then that can be given to the NMT. So then NMT is producing the results. Okay, so NMT is producing the result, but the thing is that one more thing is happening. What is it? So your output sentence may suffers a problem which is known as a word sense disambiguation. Okay, what do you mean by word sense disambiguation? So we already explained there is a multiple meaning for the word. Okay, so according to the situation, what is the correct meaning of the sentence of the translation? You have to predict that one. Okay, in order to predict that one, you had to apply, you had to perform a words dense disambiguation module in both language pairs. Okay, so normally we are going if source and target, we are taking in case of target sentence only. Okay, we can go for the word sentence version in the target sentence. In here it is a bidirectional system, that's why we are going for both. Okay, Sanskrit disambiguation and also Malayalam disambiguation. Malayalam word sense disambiguation. But normally we are source to target, we are applying word sense disambiguation in target sentences. Why? Because target is the important thing. No? So from the target language, you have to identify the meaning. So the target language, you have to go for the word sense disambiguation. Okay. So, but before words, in order to perform, this is a word sense disambiguation module. So in order to perform the word sense disambiguation module, the word sense disambiguation should be done, can be done if the corpus is tagged. What do you mean by tag? Post tagging. That means you need to identify whether the word is a noun, verb, plural, that kind of thing. So that is generally known as a post tagging. That is another application. So before word sense disambiguation, you have to go for some tagging mechanism, post tagging. Okay, that you have to do in both languages. Here I am going in Sanskrit and also in the Malayalam language. Okay, then there is a word sense disambiguation, and this is producing the result. And final thing, after receiving the result should be in a separated form. Why? Because it is morph analysis. Here it is morphology analysis. So you have to apply a reverse of morph analysis, which is known as a morph generation, in order to produce the output sentences. Okay, so these much of modification should be done in order to produce a efficient translation. Okay, so if somebody is going to research in machine translation, you can think about your source and target languages, and you have to identify all the morphological and syntactic rules assigned with the source and target languages. You have to identify that rules. Accordingly, you have to form the set of modifications in the NMT. Okay, otherwise NMT, the vanilla NMT will report a very less results because of these reasons. Directly mapping it is not possible. Okay, and the translation efficiency normally we are measuring with the help of a score which is known as a blue score. Okay, so this is calculating with the help of some n-gram probabilities and all. So if the blue score is getting something around 40 plus, okay, 40 plus, it is a well translation. Okay, good translation. Okay, that we'll discuss. Okay, so the thing is that I already told you there should be a corpus. Somehow you have to define your corpus. Parallel corpus should be there. So here you can see in our data there is a Sanskrit and Malayalam sentence. It should consist of 2,54,700 data. Okay, because this much amount of data it is needed in order to train a neural network. If you are going for a research, you have to identify the source and target language, and you have to identify whether the ready-made corpus are available. If the ready-made corpus are not available, you should generate your corpus according to some mechanism. Okay, you have to search in different books and all. You have to manually construct sometimes it may not be available, that type of thing. Anyway, the sentences, the corpus size cannot be less than 1 lakh. It should be more than 1 lakh. Okay, at least 50,000, otherwise it will never give a result. Okay, this is the we explained here. So here before I told you that there is a character word embedding, joint character word embedding. You can see that this character embedding it is coming, then some character level convolution, then concatenation of character and word embedding, and that concatenation matrix it is given for the NMT. This is we are incorporating convolution operation here. Okay, in order to represent join, in order to join the character and word embedding. Okay, so this is, you can see join character and word embedding producing a 9. You can see this one, it is producing a good accuracy. Okay, so then morphology I already discussed. Morphology means you have to apply morphology in both the source and target language. According to your language features, you have to identify the morphology. Here it is a Malayalam morphology, so you have to identify the different types of morphological rules which is available in the Malayalam language and do the morphological process. So according to your language, this is not important. Why? Because this is according to your language, you have to define the morphological term. Okay, then Sanskrit language, you have different types of words. This is only limited to that language. That means if you have your own language, you have to identify different types of categories of words in that particular language. Here in Sanskrit, you can have different types of words like subandha, tiranda, kridanda, tadida, samasas, etc. So that type of words that may be entirely different from your target language. Okay, so that your target language may consist of different set of words. You have to identify those words, and you have to identify how morphology can be done in that particular word. Okay, so here I'm just showing that these type of things are available in the case of Sanskrit languages. Some subandha words, you can see different types of subandha words here, and no need to worry about this one, no need to study this one, because your target language may be different. Okay, so in that target language, you have to identify the set of words. Okay, so here another word is known as the Tiranda words. This is a rule of forming Tiranda words, like something is there. Okay, so I'm not going to in depth of this type of thing, because we are not interested in the language features. We are interested how we can formulate these words with the help of a neural network. Okay, so these are another words available, number of words data sets, and you can go for the morphology of different types of words. And this one, this is the, you can see. So you can see a word model. Okay, so for Subandha is a one type of words that is available in the Sanskrit language. For this one, you can you can see a Ramena. This is a word in the Sanskrit sentence, and this should be splitted Rama. Okay, and there is a model. You can see this is first character embedding model. Then we are going for a bidirectional LSTM model. Okay, so these words are this chain in such a way that it is character by character it is giving. Then there is a softmax layer, and the softmax layer is outputting Ram and Nam. So all the words available in the Subandhas are trained in this architecture. Okay, using the same architecture, these type of words. Okay, Subandha rule may be same. All the Subandha rules, Subandha word rules should be incorporated in this model. So this model is able to identify any new word it is coming. Like this, you can see another model which is known as Tinanda words. Tinanda words are, you can see in explanation, Tinanda words are more complicated. So in Tinanda words, this is character embedding, then again bidirectional LSTM. This is a two-step process. Why? Because these words actually Bhavadi, it is Bo plus Ati. Then this is a syntactic feature of Sanskrit language that you can be implemented with the multi-stack operation. So first bidirectional LSTM is going here, and next processing, next hidden layer, it is going to the next processing. Okay, then finally it is softmax, it is producing the output. Like this type of model is producing. Like this, you can see another Tadida words like Putra, Pautra. This is according to the language feature, you can define this one. Also, this is for the Samasa words. Okay, then Malayalam word morphology, Parayunnu, Parayu, Nu. So this is this type of splitting should be done. Okay, so all the words are trained in this type of architecture. Okay, so this is what we are interested. So this is generally known as a hyperparameters. Okay, so hyperparameter means first one, it is an embedding size. Embedding size means word vectors and character vectors are word embedding and character embedding we already discussed. So what is the size of this vector? Okay, so that is also a hyperparameter in which you need to set the embedding size. Okay, which sometimes the embedding size may vary. So you can design your embedding size in such a way that it is producing the maximum translation efficiency. This is also a number of hidden layers. Number of hidden layers in the unit also you can vary accordingly, and you can plot the graph and you can see what type of architecture it will give the maximum translation efficiency. And output, we are always going for the softmax, already discussed. It is a probability distribution over the output. Then loss function in the neural network, we discussed the loss function. So different types of loss functions are available. Loss functions are we are using categorical cross entropy loss function and optimization algorithm, learning rate eta, and that is here it is 0.01. This you can change and you can according the all the hyperparameters, it is depends upon your data. Okay, so according to your data, you can tune your neural network in such a way that it is giving the maximum translation efficiency. And batch size means how many words, how many sentences you are taking in a batch. Okay, that is also you can change, and number of epochs also number of you can change. Okay, so you can change the architecture according to your data and feel what is happening, and you can plot the translation efficiency in each and every case and find the best architecture which is used for the classification. That is normally what we are doing. Okay, so this is just an illustration of the different modules. And after that one, we need to synthesize more synthesis. You need to generate back. Already explained in the previous slide, you have to synthesis. Morph generation is needed. So morph generation is the same like architecture can be used. You can see this is a morph generator, just reverse process of morph analysis. Okay, just input and output are changing. Model is same, architecture basis is also same. Okay. So then what is another one? It is known as a post tagging. Why we are going for post tagging? So in order to implement word sense disambiguation, we have to post tag. Okay, we had to part of speech tagging. You have to tag the sentence. So this post tagging, before there are rule based technique, now we can go for the deep learning based method for the post tagging. Okay, you can think about these are the some of the tags available in the Sanskrit post tagger, and this is a number of tags, and this is a measure that we are going for post tagger. Okay, this is just an illustration, but the thing is that you can use a deep learning based method for the post tagging also. Now, previous case there are role based and statistical based method, but post tagging can be done also with the help of deep learning. Okay, so these are some results and word sense disambiguation. Okay, so after outputting, you can see some sentences examples. These are some ambiguous sentences in Sanskrit languages, and also there are some ambiguous sentences in the Malayalam sentences, and you have to identify these set of sentences. And from the set of sentences, if some ambiguity is there, there should be a mechanism. Okay, you can go for different mechanism like rule based or statistical based, also neural network based, also some evolutionary methods. Here I am using an evolutionary word sense disambiguation to ambiguate the words. Okay, so after that one, you can go for the NMT model. Okay, that is already discussed, NMT model. So first pre-process, then different architecture, NMT with the transformer network. We already done this, we already discussed everything. Then you can go for the translation efficiency. Okay, so manual evaluations are there. So the thing is that after producing the translation, you can evaluate the result both automatically and manually. If manually means you have to identify some person and check whether the translation is correct or not, and you are assigning some scores. Okay, these are the some scores assigning mechanism, and also you can see the scores. Okay, then another one, there is I already told you there is a blue score. This blue score will give the results. You can see without any mechanism baseline NMT, it is giving 36.54. Now transformer NMT, you can see it is increasing 38.15. Then some pre-processing, you can increase 38.62, and character embedding, you can come 39.87 like this. And finally, if you are incorporating morphology, it is increased. And finally, if you are incorporating word sense disambiguation also, these scores are coming to high. Okay, so this type of improvement can be done in the neural machine translation. Okay, so this is in the help of, this is with the using the Sanskrit and Malayalam language pairs. Okay, so we discuss, I think, almost all the techniques that is coming under the neural machine translation, it is covered. Also, we discuss with limited amount of time, we discuss neural network and also some architectures, different types of natural language processing mechanism, and how can you do this natural language processing with the help of different networks. And also we compared the performance, and for this a comparing mechanism, and also we took some case studies like two languages. Don't bother about these two languages, because why I am going in not depth of this is that your source and target may be different. Okay, so according to the source and target, the rules may be different. The syntactic and semantic rules may be different. But the architecture ways, it is neural machine translation, it is okay. That is already we explained all the architecture, and just I am showing how these type of things can be inputted into the architecture. Okay, but the thing is that before inputting into this architecture, you have to identify all the syntactic and semantic rules, semantic aspects of your language. That is your duty to find all the semantic and syntactic aspects. That should be something great. Okay, if you can do that one. Otherwise, the conclusion NMT will never produce a good result. Okay, if you want to use NMT for Indian languages, then pre-processing and post-processing should be done. Okay, so that is the thing. Okay, Namita, I think it is enough. Then, if you anything you can discuss.
Yes, yes, sir.
Any doubt till
Participant,
now? Actually.
participants, you can ask your queries now.
Okay, one more thing I need to incorporate is that one research problem I can suggest you is that I think you might heard about multi-modal. Okay, more than one modality you can it in the translation process. For example, here we are processing with the help of text. Okay, text processing. Now you can come up with the same corpus, you can convert into speech or something like that. Okay, then you can incorporate speech, and this speech should be given to the NMT model. Okay, so how can you give this speech to NMT model? That is a different thing. Why? Because NMT model in the text we can convert word to vector. Okay, word to vector is there, but in speech it is not possible. It is not words. Okay, speech are constructed with the phonemes and all. So how to convert this speech to vectors? Okay, so that you can do with the help of different thing that you can do with the help of some Fourier transform and wavelet transform. And using wavelet transform or Fourier transform, you can convert your word to convert your speech to vectors. Okay, and that thing you can give into a neural machine translation. The neural machine translation is trained with the help of these vectors. Okay, that vectors means speech vectors. Speech is converted into what? Speech is converted into vectors with the help of different for a transform domain. It should be converted into a transform domain, frequency domain, and then process that data and train the neural network and feel the output and take the output and compare the result. You can compare the result of text, and also you can compare with the help of speech also. Okay, then you can see that it is a multi-modal processing. So this type of research also is possible. Speech can be given to the neural machine translation. Okay. Okay. Anything? Any doubt?
Participants, you can ask your queries.
Okay, now if no queries, we can wind up, isn't it? Okay.
Sir, actually, someone is trying to say something. Sir, wait for a minute, sir. Sir, someone asked something in chat box.
Okay, that I can share you. So actually, that corpus, the parallel corpus is not uh, created. So I will share you. I will share you the link. Okay. So please take my mail ID and I will send you that link. Okay. So Namita, you can give the mail ID and all. Okay.
Okay, sir. Okay.
The image captioning and all we can use CNN. Okay. Convolution neural network is good for image classification and all. RNN normally we are using text processing. Okay, text processing because uh, it's text processing you can see sequence by sequence, word by word it is coming. So if you are going for many image or video something like that, you can it is better to go for convolution neural network. Okay. So the necessary steps to include the corpus is that. So that depends upon your source and target language. Okay. So my suggestion is that suppose your translation is done in the Indian languages. Okay, I don't know which language you are going for. So if you are going for Indian languages, maximum sentence length can be limited to 10. Okay, one thing. Don't make the network more complex. Okay, while giving more complex sentences. Like a sentence consists of uh, 30 or 40 words. It may not be possible to identify the neural machine translation because our languages are morphologically rich languages. Okay, so word order also may be different. So try to make a translation system which can be utilized for maximum 10 words in a sentence. Okay, that is the first thing. And second thing you have to design is that again depends upon your source and target language. For example, here in my uh, this one my work, so you can see Sanskrit and Malayalam. Okay, so the one advantage is that you can frame the Sanskrit in any order. It is a free word order language. So one language you can fix one order. Okay, that means Malayalam it is following this order. Okay, that you cannot alter. Okay, for example, English, he is running on the road. You cannot change the order of the sentence. That means he on the road, you cannot write. Okay, but sometimes if it is possible to rearrange the words in some language, some source and target language, that should be fine. So suppose Sanskrit to English. Okay, English it is alteration it is not possible. Okay, word order you cannot change. So you design the corpus in such a way that English is following the normal word order, and while making the corpus, rearrange the Sanskrit sentence in such a way that if it is possible to make a one-to-one contact with the source sentences. Okay, so if it is a corpus, if you can make a one-to-one correspondence between the source and target word, it is fine. Okay, so that is the second thing you had to think about. Okay, sometimes in most cases readily available corpuses are not readily available. Okay, some foreign languages or some other languages corpuses are available. Sometimes only one corpus may be available. Sometimes if you can have Malayalam corpus only, but the corresponding targets may not be available. So you have to manually construct. Okay, so in your research work, the corpus construction is the main thing. Never think of implementing a neural network without a size of corpus at least 50,000. Again, 50,000 it is showing some errors. If it is 1 lakh is good. It is going for 1 lakh sentence. Then only. Otherwise, the thing is that you cannot compare the output. Okay, it may lead to some errors. You cannot take the measure. You cannot include some linguistic features into the language. Okay, why? Because it is not producing the actual results. It is not showing the actual results. It may some errors in the result. So then how can you interpret that result? So So the corpus size should be same. So three things in order to make the corpus is that minimum 50,000. Okay, if you can make a corpus of 1 lakh, that is well and good, and then make a simple one. Maximum word length can be limited to 10, and also if you can design a corpus with one-to-one correspondence, that is also well and good. Okay, then it may be easy to do morphology and all. Okay, and the corpus should be morphologically separated. After that is the next step. Okay. Now it's audible, no? You are getting. Hello, is it audible? Okay. So,
Audible, sir.
Namita, you can. I will share you the slide. Okay, so you can give the slides and my contact to this. Okay, my
Okay, sir.
mail ID and all slides you can give. Okay.
Okay.
Yes.
Hello, sir. Hello.
Yes. Uh, tell me, man. Tell me. Okay.
Uh, so I have one doubt. For how can we prepare or generate the word embeddings for the Sanskrit text, or what are the feature, or how can we select which semantic features we have to include for generating this word embeddings for Sanskrit?
Okay, so the word embedding you are designed with the help of different aspects. Okay, so you can decide what are the semantic features should be included in the sentence. Word for a particular word. So not only the Sanskrit sentences, whatever may be your sentence, your language, you can design your what type of feature should be incorporated in the word embedding. Sometimes it may be only the gender information. Sometimes it may be a gender information plus noun post tagging information. And like this, you can design your criteria. You can design your parameters. How many factors should be in the word representation. Okay, so according to that, you had to identify some linguistic features. These are the features that features can be incorporated in a representation. In Sanskrit sentences, we have different set of parameters. That parameters is included in this one. Okay, that may be some word ordering, some ambiguous sentences, and also some tagging information, some gender information, some subanta tinanta words. There are some special issues. Okay, special cases. Some tinanta words, some rules are there in the tinanta words. That type of information it is incorporated in the word representation.
Okay, sir.
Okay.
My doubt is that how can we incorporate these features to this neural network or this word embedding
So
algorithm?
what you can so is that you take a word embedding algorithm. Okay, you can take a
Uh-huh.
word embedding algorithm. The ready-made word embedding algorithm you can just check. Okay, so the
Uh-huh.
standard word to vect and glow methods are there. Okay, so
Yes.
you just analyze the code how they are doing that one. Okay, there is a code available.
Uh,
Make that code, you study that code. Okay, according to that
uh-huh.
code you can design from that code you can identify how these features are incorporated in that one. Okay, then if you want to add some more features, according to that you can write code in Python or something. You can add whatever features you want, you can incorporate in that one. The
In that
programs are
one. Okay.
available. Yes, programs are
Uh,
available. So modify your program according to your feature. Okay.
okay, sir. Is there a and I think there is an INLTK for Indian languages in Python, isn't it?
Yes, that you can use.
Okay, in that, whether we can add these semantic features,
Yes, definitely
whether
you
we
can
can
add. Semantic features means if you want go for some, especially in Sanskrit sentences or something, you can identify your own semantic aspects. Okay, you can identify your own suddenly you notice that with the help of your data, because your data is different from the already available data. Okay, so in your data you suddenly you come across with some new idea, some new representation, some new ambiguous words are represented, and how can you solve this type of words, then that information you can add in your semantic feature. If you want to add more from your data, that is also possible.
Okay. You already
That you
told
can do
that
with
there
that.
is a parallel corpus generator. Parallel corpus is there for Sanskrit and Malayalam.
Parallel
And
corpus is not there. I develop a parallel corpus for this one. I got only corpuses for Sanskrit sentences. Okay. From the site, from the link available, you can see there is a Sanskrit sentences only. So there is some model which is known as a Oliver Helving model. Then Oliver Helving model, there is Sanskrit corpuses are available. Only Sanskrit corpuses. From the Sanskrit corpuses, and also we can take different sources. You first what I did is that I constructed only Sanskrit corpuses from the various sources. Okay, that sources I mentioned in the slide from where I this. And what I did is that manually constructed the corresponding Malayalam sentences. So how we did is that take a Sanskrit sentence, approach some linguist, okay, those who know those who knows both Malayalam and Sanskrit, and manually you have to write each and every sentences. Okay, for the corresponding Sanskrit, what is the Malayalam sentence? Then if you are doing that one, it is good. Why? Because you can frame the target language according to the word order of Sanskrit language. Okay, so
sir,
manually,
can you share some sample of that Sanskrit Malayalam corpus
yeah, sure,
you
sure.
created?
I will completely. I can share you after some time because of some reason. So some data set I will share you. Okay, because I
Okay,
am going
just
to release this
some.
going to release this database only after some time. Okay, within 6 months of time I can it may be available in. You please contact me. So I will tell you which site it is available. Now today I cannot actually reveal this database. But I can give you samples of data set like 100 words or something like that. Okay. So entire 2,58,000, I think I can share only after 6 months. Okay. That I will do.
Okay, thank you, sir.
Can an RNN model can be used to analyze the captions generated from CNN model? Yes, that is possible. Okay. From the CNN output, you can go for a caption analysis on using RNN. It is possible. Definitely it is possible. This is for Arathi Gopinath. Okay. Anything else? Okay, Namita, you can share my details. Okay, my slides and all, I will share you over the mail. Contact
Sure,
details and
sure.
everything you can share. Okay, please
Okay.
approach the coordinator for the details. Okay. So shall I wind up, Samita? Is it okay?
Yes, sir. Thank you so much for such an enlightening session. Thank you so much. And
Okay.
I will definitely share your details and everything with all these participants, all the required participants. Okay, sir. Thank you.
Okay, Namita, I am leaving. Okay, thank you. Thank you very much.
Uh, I know all dear participants, and we are actually planning to reschedule our today's session because for managing the time, and actually our feedback and valedictory sessions are planning from 4 p.m. to 4:30 p.m. We know that this is the time to leave. This will be the time for leaving from the college actually. So we are planning that session now for a period of some 20 minutes. So I welcome some of you from the participant side to say something about this session, our FTP. I welcome some of you to say some feedback about our FTP session. Please, someone come and say something about our FTP. Actually, I am inviting some of you to say something about our FTP session. We need some feedback from your side.
Good morning, ma'am. This is Aarti.
Hi, ma'am.
All the, yes, ma'am. All the sessions were very nice, ma'am. Actually, we had the hands-on sessions too. It was very nice. Most of the FTPs they'll be handling only the theory sessions, but here it was very useful for us. We had many hands-on sessions, and it was very useful, ma'am. Thank you so much for arranging such wonderful resource persons. Thank you, and it would be helpful if you send the PPTs and the contact details, or at least the PPTs, ma'am. It will be useful for us.
Of course, ma'am. Please WhatsApp me personally. I will
Yeah.
share that contact details and some other PPTs, everything
Okay.
with you personally.
Yes,
Please
ma'am.
contact me personally.
The generation of the models, that's the hands-on sessions was very good. And if it
And
is
actually, we are,
being
ma'am. Actually, we are planning to deliver every recordings. We are
okay,
actually we have a YouTube channel, so we are actually uploading all the recorded sessions in that, and after
okay,
completing it we will provide that link to everyone of you. Okay.
okay, ma'am. Okay, thank you so much. It was a very nice FTP, ma'am. This 1 week, it was very
Thank you.
nice. Thank you so much.
Okay, ma'am, thank you so much for your words.
Good afternoon, ma'am. Myself Shivkumar from BMS IT Bangalore. So for me, this workshop was given an introductory part of understanding of the this content. So this is first time I am attending this research based discussion. So it was very nice. All the resource persons are given a good content to us. Thank you, madam. And also, I would like thanks all organizers to arranging such a wonderful workshop. Thank you.
Thank you, sir. Thank you so much for your kind words. Anyone else?
Good afternoon, ma'am. I am Sridhiva from College of Engineering, Adur.
Okay.
Actually, first of all, I would like to thank the coordinators for arranging such an FDP. Actually, I am eagerly waiting for an FDP like this especially in NLP. Actually, the NLP FDPs on advanced NLP is rare. This is the first one I am attending the FDP on NLP. So, thank you, coordinators, for arranging such an wonderful and innovative FDP. And due to exam duties, I couldn't attend some one of the session. Anyway, all the sessions were interesting and useful for us. Thank you uh, all for the help and coordination.
Thank you so much, ma'am, for your words. And actually, we are planning for a YouTube channel, and we will upload every recordings, all the sections. Okay, ma'am. After that, we will share that link with all of you. Then you don't worry about that missing session.
Okay, thank you, ma'am.
Thank you so much, ma'am. And anyone else?
Is there any assessment session? Is there today?
Yes, sir. We will provide you some questionnaires after some time. After completing the other session, also we will provide you some questions.
Okay, thank you.
Now I request all of you to turn on your camera for a while so that I can take some snaps. Please, everyone, turn off your camera for some time. Srideepa ma'am, are you there? Aarti ma'am, are you there? Okay.
Actually, I'm at college. Some light issues are here.
It's okay, ma'am. It's okay. It's okay. Okay, ma'am. Thank you. Now you can turn off your camera. Excellent. So it's my privilege to propose a vote of thanks and acknowledge the contribution of those who worked really hard to make this event possible. On behalf of VJC and the entire fraternity of this institution, I extend my sincere thanks to the MIT for making this event a success. I extend my hearty vote of thanks to our beloved principal, Dr. Benny Joseph sir, for his support and guidance. Thank you, sir. And I extend my sincere vote of thanks to the HOD of Computer Science Department of VJEC, Dr. Jitu V. Devasya, for her effort for making this event happen. Thank you so much, ma'am. Now I extend my vote of thanks for all the non-teaching staff and technical staff for their hard work and the coordination. Thank you so much all. Now I extend my hearty vote of thanks to all our resource persons. We have no words to offer gratitude for them because their deep and intellectual way of imparting knowledge have added to the glory of this event. And last and but not least, I thank all the participants. Without you, this event would not be a success. Thank you all. Once again, I thank one and all wholeheartedly. Thank you so much. So now we can leave the session and our next session, no change in that session. Next session will start from 2 p.m. onwards, and that session will be a hands-on session, and that is going to handled by Premjit sir. Okay, now we can meet again from 2 p.m. onwards. Okay, thank you.